Hello, Rohan sir. Have you joined, sir?
Yes, sir. Yes, sir. Yes,
Yeah,
sir. I
yeah,
joined.
yeah, yeah, sir. We wait.
Sure.
Good morning, all the participants. Today is the sixth day of machine learning and pattern recognition phase two. Today, Mr. Rohan Patil is with us for conducting the session of deep learning, uh, a deep dive, its theory and hands-on. So, two sessions will be conducted by by Rohan Patil sir. Okay, so Rohan Patil sir is with us. So I am just handovering the session to Rohan Patil sir. So over to Rohan Patil sir.
Sure, sir. Thank you.
Right.
Um, yep. Good morning, everyone. And thanks a lot for joining today also. I think yesterday's session was pretty well convinced about ensemble learning, and I received a couple of comments from you guys after the session. So glad to see that you guys well connected with it. And so today, the session that I want to have with you guys is a deep dive on the deep learning domains, right? So there has been much of a talk about deep learning, right? And many of the sessions which I saw across during this five days of this lecture series was somehow focused on deep learning, right? There were some talks, I guess, about GANs, about CNNs, about artificial neural networks, and so on. But when we try to learn more about this deep learning domain and more specifically about the neural networks, we need to get our mathematics clear, right? So all this is a play of mathematics. The more you clear out your basics, the more you will be able to understand the concepts in this domain, right? So today what we are going to do, I hope my screen is visible. Please let me know if it's not visible, right?
Yeah,
So
yeah.
okay,
Yes.
thanks. So today what we are going to do is we are going to dive deep into some of the basic concepts of deep learning, right? I'm not going to cover the the how the CNNs work, how the CNNs are winning challenges of ImageNet data sets, and how the recent neural networks are going on and winning some good competitions and using in products and so on. What we are going to do, or what we are going to learn today, is the basics of deep learning, which will be very important for you guys, for those who are stepping newly into this field, and for those who are, even those who have worked in this field for a few years. It will be a good refresher session for those guys, so that the concepts that we are going to learn today, if we are very clear about those concepts, you'll be able to understand any neural network or any research paper that has been published in the recent times about this domain, right? So everything lies into these mathematical concepts that we are going to see today. That will be about the theory part, and there will be also a small practical hands-on session where what I'm trying to demonstrate in that case is the Python libraries that are used usually to train the models, or say to evaluate the models. These are very high-level programming APIs, right? So you don't get to understand what is the underlying concept or underlying mathematics that runs behind those libraries when we simply type model.fit, right? So usually that is the sad truth today, that most of the people who are working in this domain, they are just taking some off the shelf models which are readily trained by on huge data sets. They download them, they use it for their data sets, and they just run the simple command of model.fit, and they claim success on top of it. But that is not what data science is, right? That can be done by any of the first year engineering student as well, right? What data science actually means, or what I would prefer it to say, is that you should know the mathematics, or the concepts that run behind those training concepts, behind those training of the models, how the derivatives are computed, right? How the model is trained, how the model is learning those variables, and so on. And that will be, I won't be too detailed about those things, because that will be overwhelming session for you guys. So I'll just give a brief introduction of comparing how the high level APIs that are used today work under the hood, right? We will unreveal what is happening behind those model.fit methods, and what how the derivatives are computed, and so on. right? And at the end of the session, I think that will be the last part of this session. At the end of the session, I'll also cover some of the recent trends in deep learning, right? We will see some of the recently published architectures which are making a huge impact in this domain, and they are used for various applications and are used across the industry. May it be healthcare domain, may it be some face detection in something like Facebook, may it be some data analysis on Amazon, and so on. So we will see some of the recently published architectures at the end of the session, right? So this will be a span across the basics of the deep learning till the most advanced concepts in the deep learning. Okay, so let me get started with this, right? um, when we think about the neural network, the concept of neural network, like the deep learning is basically formed by small atoms called neural networks, right? So when we think about these deep neural networks, what do we think, what do we imagine, right? It consists of at least three major concepts, right? The input layer, the hidden layer, and the output layer. You might have come across these terminologies. It's very easy. The input layer takes in the features from the data set, right? Where it may be it may be a single feature, it may be multiple features, and so on. The input layer contains nodes which simply take up the features from the data set, right? The hidden layers are the one which actually do the operations on those features, right? So as we said in the last session also yesterday, that in machine learning you have to be responsible for crafting the features for the data set that you have. But in deep learning you don't need to do so, right? The deep learning takes care, or the neural networks take care of the feature extraction step on itself, right? When we train the deep learning models, the feature extraction step happens, or the feature engineering steps happen during the training itself. So when you have a very complex data and you are not sure about how do we extract the features in such cases, the hidden layers in those data set, in those models, the hidden layers in those models take care of the feature extraction step and the activation steps in that case, right? And finally, you have the output layers, right, which will take up the values or the weights from the hidden layers, and then do some sort of a prediction using some sort of activation function or aggregation function in that case, right? So these are the three basic building blocks when we talk about a generic neural network, right? Now, what is the meaning of a layer, right? When we are saying that it's an input layer, it's a hidden layer, or an output layer, what is actually the concept behind layer? So layer is nothing but a collection of neurons, right? It is a collection of neurons. Neurons are basically the cells of the neural network that we can think of in biological aspects, right? These are the decisive units which actually takes decisions whether we want to pass on the information from the previous layer to the next layer or not, right? So each neuron in a particular layer contributes to the final decision making process in your ultimate goal of the prediction, right? So layer is nothing but a collection of neurons which you can think of, and every branch, right, every branch in each layer, right, has a weight associated with it. And what do we mean by these weights? These weights are nothing but the parameters of your models, right? So when you say that I am training a model, you're actually making the model learn the weights of different branches in those things, right? So these weights are very important. You have seen the concept of weights in conventional machine learning as well. When we are training something like support vector machines, right? Or when we are training something like a random forest or something like that, we are, say a linear regression or a logistic regression, we are training the weight or we are the model is learning the weights of those branches, or the weights of those polynomial functions, right? And these weights are very important, and these weights form the core concept of the prediction that is given out by the model, right? So these weights are something that are learned during the training process, and these are also known as the parameters of the model, right? So I put a diagram over here which kind of explains what a neuron goes through during the entire in the architecture of this the neural networks, right? So for example, if you look at this diagram, we have weights over here where we'll be taking into, say, these are the input nodes x1, x2, x3 till xn. You will have the weights associated with that, and you will have a function, an operator function, which can either be some sort of an aggregation of the weighted, which can either be either a weighted sum of these weights, or say some more complex function which can be a polynomial equation or something like that, right? So this transfer function will kind of get the weights from the previous layer, and aggregate it or operate on those weights from the previous layers and make some predictions on top of it, right? Now there is also something called as bias, which you will come across in some slides ahead as well. But these biases are very important in regularizing these models, right? So these are the transfer functions that we get, and then this transfer function is given to an activation function, right? I want you to remember these terminologies, like the inputs, the weights, the bias, the transfer function, and the activation function. These are very important terminologies or conventions for those who are new in this domain, or so for those who have just learned something about machine learning but have no deep knowledge on deep learning. It is very important to learn these terminologies and understand what these means, right? The inputs, the weights, the transfer functions, and activation functions are very important concepts, right? What do you mean by an activation function, right? So when we when we get the output from the transfer function, which can either be a simple weighted sum of the weights from the previous layer, the activation function is is a decisive function which decides if the neurons should be activated or not, right? When I say that the neuron should be activated or not, it means that whether the neuron should give out the something like a binary value like 1 or 0, right? Or maybe it can be either be a non-linear activation function as well, right? We'll come to the linear as sorry non-linear activation functions, differential activation functions, and so on in some slides ahead. But these are very important concepts because these determine whether the neuron should be activated or not, whether the neuron should be, in layman terms, whether the neuron should be put on or off, right? So these are the core concepts that form the basics of a particular neuron and its weights and the layers and something like that, right? And this, the diagram on the right hand side, which I put over here, is what forms a neural network, right? What you saw on the left hand side was a very short version of this diagram. Here is a very extended version, not very extended, it's still a two-layer network itself, but still this is an extended version where we can actually see an input layer being there, a hidden layer, and an output layer, right? And you can see on top, I've taken this diagram from the references that I put at the bottom of this diagram, so please go and check it out if you want to learn more about them. But you can see that these are the three layers which I have been talking about the neural networks, right? So the input layer takes the inputs from the different features or the different data points that we have, right? And then we have the hidden layer, right? Which the neurons at the input layer can be connected to these hidden layer neurons in any which way possible. So for example, this is a fully connected layer. So every neuron in the previous layer is connected to every neuron in the next layer. So such layers are known as fully connected layers, right? So these are connected to each neuron in the next layer, right? You can see the weights noted down on top of each of the branches. That's a W11. It is the weight from the first neuron in the first layer to the first neuron in the second layer, right? W12. It is the weight from the first neuron in the first layer to the second neuron in the second layer, and so on. So you can see these weights present on these branches, and these weights are very important. As I said, these weights are the something which are learned by the model during training, right? So, and you can see in each of the neuron there is a function f of theta, right? So theta is nothing but the usually theta is used as a convention of the parameters of the model, right? So theta is usually used in many of the research papers which you will come across. If they want to mention the notation for the parameters of the models, they use the convention of theta. So theta in this case is the parameters of the model that are trained, right? So f of theta will be some function which will be used by the aggregator function plus the activation function. They are together noted down over here as sorry f, right? So f of theta will give you the activation, and a1 will be the activation given out by this, right? So this is the same story across all the neurons in the hidden layer, correct? So after that we have an output layer which takes in inputs from each of the neurons in the hidden layer, and again there are weights associated with that, right? There can be multiple hidden layers as well. Again, when we talk about deep neural networks, then this is a neural network, and when we talk about deep neural network, there are multiple hidden layers possible, right? And there are even nested hidden layers possible. So it can be a very deep neural network, it can be a multi-channel kind of a neural networks, and so on. But in this case, so we are taking the weight from the previous layer, that is the hidden layer, and we are getting this output neuron, the neuron in the output layer over here, where it works on function g of the theta, right? And it gives an output called OK. Okay. So you can see the equation on top of each layer, right? So if aj forms the output of each of these neurons, What we are doing over here is f of, as I said, the function in each of the neuron is f in the hidden layers, right? So f of summation of I to 1 to n wij xi plus bj, right? So every this is a simple weighted sum of the previous layer activations or previous layer values, right? And then we are adding bias term to it. This is the bias term which I have been talking, right? This is the bias term on the left hand side picture, which we are adding in this case, the bj, right? So what we are doing is we are making a weighted sum of the weights from all the neurons in the previous layers, because all the neurons are connected to this neuron, right? And then we are adding the bias term to it, and that forms the output of each neuron. This forms the output of each neuron in the hidden layer, right? Simple. This is a very simple operation that has been done over here, wijxi, right? And this form the basis of the computations that happen across the neural network, right? And we add the bias term to this. Similarly, in the output layer, the equation can be seen like this. OK equal to OK means the output given out by the model. It is taking in the function called as G. In this case, you can see in this neuron, the output layer neuron, the function used is G, right? And the similar equation can be seen over here with just a change in the terminology that J runs from 1 to M. Right? Why 1 to M? Because the M depends on the number of input that are being received by the output layer neuron. So J runs from 1 to M, WJK AJ plus BK. Right? So it is taking the weighted sum again from the previous layer neurons and then adding bias term to it and giving out the prediction. Simple. So this is a simple a neural network architecture which you can see. This forms the basis of various computations that come across when we talk about these concepts, right? I want you to remember these concepts when we are talking about such neural networks, because this will be very important for us when we will be going deeper into the neural networks in the sessions ahead, right? Two of the most important concepts that form the basis of the computations or the training process of a deep learning neural network are the gradient descent algorithm or the gradient descent operation and the backpropagation. You take any course in deep learning domain, you take any book related to this deep learning, you will find a separate chapter on each of these topics, right? Because these topics are the backbone of your entire training process that happens when you train a model, right? These concepts or these are simple mathematical concepts, nothing fancy about them, no rocket science in that. These are simple derivative based concepts, right? You must have learned derivatives. These are simple concepts on derivatives, but these form the backbone of even the strongest neural networks that are out there today, right? So these concepts are worth remembering and understanding, and we should see how these concepts are used when we train a neural network, right? When we say that the model has achieved convergence. Convergence is usually used as a term when we say that the model has learned the or fit well to the data set. We say that the model has converged. What do you mean by the model has converged, right? This all these terminologies come from these two main concepts: the gradient descent and the backpropagation, right? Very important concepts, and I want you to remember these concepts when we will ahead, right? So gradient descent, right? We'll start with gradient descent. It is an iterative optimization algorithm, right? You can there are many optimization algorithms out there. So there are many variants of these gradient descent algorithms that have been coming up. But the basis is always this two steps of the gradient descent algorithm, right? And what do we try to attain with this optimization algorithm? We try to attain the global minimum, right? This is again a mathematical notation or mathematical term that you must have heard when learning calculus in your high schools or plus two. So when we have a function, right? When we have a function and we want to find out the minima of that function, what do? We take the derivative, right? And there are derivatives as well. There are, say, the first order derivative or the second order derivative and so on, right? When we say that I want to find out the minimum of this function, we take the derivative of that function, right? So the simple two steps are there in the gradient descent algorithm. First one, it computes the slope of a function at the current point, right? Say if you can see the diagram at the bottom that I put over here, and this black point is something which we are at currently, right? Say for example, we are at this black point, black dot or a big black circle that you can see over here. Here we are, right? Here is what we start with, right? And we want to take the gradient descent route. So what we do, we compute the slope of a function at this current point, right? So this is the function which I'm talking about, and this is the slope that I have been finding out, right? So this is the gradient. This dotted line forms the gradient or the slope of this function at this current point. And what we do, we move in the opposite direction of the slope by a value which is computed by some operation, right? We move in the opposite direction of slope. So we are moving downwards of this slope, right? And what is the step by which we are moving, right? Remember the word step. Step is usually a word which is used in the deep learning or in any machine learning algorithm by which means that how or what is the distance by which you are moving towards convergence. What is the step? We can you must have heard different notations like step, that like the learning rate, what is the step size, what is the step weight, and everything. So step is a very important term. It determines how fast or how slow are you wanting to move towards convergence, right? So this is a step that we take towards the negative direction or the opposite direction of the gradient that gets calculated, right? Simple two steps, and this forms the basis of gradient descent, right? It is an iterative process. We go on doing so until we reach convergence, until the value doesn't change at all, right? We go or change this very negligibly, right? We go on doing it iteratively until we reach convergence, right? Uh, so that forms the basis of gradient descent, and there are various variants of the gradient descent algorithm as well, right? You must have if you just Google search what is a gradient descent, you will see variants of gradient descent as well. Something like a batch gradient descent, something like a stochastic gradient descent, something like a mini batch stochastic gradient descent, which is a combination of two algorithms. So when we talk about batch gradient descent, right, what we do in that case, or say what we do in the stochastic gradient descent is we take in random samples, and in each sample in the data set we go on updating the weights of the model during training, right? That is something called a stochastic gradient descent. So we take each sample randomly from the data set and we go on updating the weight. When we talk about batch gradient descent, we take batches of data from the data sets, right, and update the weight according to that. But what do we do when we take mini batch stochastic gradient descent? Mini batch stochastic gradient descent is the most widely used version of gradient descent out there, right? We will see in the practical hands-on session as well that we will train a model with mini batch stochastic gradient descent, where the weights that are updated of the model are updated after every batch, which is randomly selected from the data set, right? So that's why we call it as a mini batch stochastic, as we saw yesterday also in ensemble learning session. The stochasticity basically means randomness of the subselection, right? So mini batch stochastic gradient descent basically means selecting the mini batches randomly from the data set, and then updating the weights based on that using gradient descent optimization algorithm, right? So as I said over here, random batches are selected and weights are updated for each of that batch, right? Again, you can see that this diagram very beautifully explains. I've taken this diagram from Medium. Very beautifully explain what is the step that have been incremental. So every arrow, at the end of the arrow becomes a step, right? It is a step that we go increasing, and then we achieve the minimum of this function, right? This is where we want to be. This when we are solving any optimization problem, see any model or any machine learning model or any deep learning model will try to solve an optimization problem, right? And the problem where we want to find the global minima of a particular function, right? When we find the global minima of the particular function, we say that we have achieved the convergence or we have achieved the optimized solution for that function, right? So if this line is what we is what we can observe over here, and this is where we want to be, right? This is where we want to achieve that this will be the minimum of that particular or the minima of that particular function, right? So what we do here is we start with black dot over here. You find the gradient at each step. We go in the opposite direction of the gradient by some value called as step, right? And this step will help us achieve the global minimum, right? There is also a concept related to this, which I want to bring out over here is learning rate, right? Learning rate is very important concept or a very important parameter using during your deep learning training process, right? Any deep learning model you try to train, right? It can be a single layer, it can be a two layer, it can be layer, or it can be multiple layers as well. Any deep learning model that you try to train will require a learning rate parameter to be passed to it, right? Now what is this learning rate parameter? So this learning rate parameter determines how fast or how slow Do we want to achieve the global minimum, right? When we try to update the weights of the parameters of the model during training, update the weights based on this learning rate, right? And there have been different scheduling processes of this learning rate, right? Say I can start with a constant learning rate. Okay, that is the most crude way of finding of finding the global minimum. Constant learning rate. So if you are running your training of the model for say 10 epochs, right? Or epochs basically means one iteration where the entire data set is seen by the model, right? So during training, and we do this multiple times, right? So if you say that a model has been trained for 10 epochs, that means the model is seeing the data set, the complete data set 10 times during the training, and it is updating the weights based on that. Okay, iterations are something different, or steps per epoch is something different. But anyway, when we say about epochs, epochs basically means the number of times the data set is passed to the model for updating the weights. Okay, so when I say that I'm training a model for 10 epochs, it basically means and if we start with a constant learning rate, right? So that means that the learning rate is not going to change across the 10 epochs, and it is going to stay the constant, right? So what will happen in that case? Is it going to be of any good use to us? No, right? Because see, when we start from somewhere around here, where the black circle over here is, and if you want to go over here, you may observe that this arrows, the length of the arrows are decreasing as we are moving downwards. And why is it so? Why has the author of this blog or the maker of this diagram has given arrows in such fashion, right? Because if we set the learning rate constant, the size of the arrows is going to stay the same pictorially. What does it mean mathematically? That the steps that we are going to take, that the distances that we are going to cover, that the values that we are going to use for taking the step ahead towards minima are going to stay the same, right? So in that case, we won't reach convergence, because we can go very close to the minima, but when we go very close to the minima, we'll be again jumping over here away from the minima. Then again we will be jumping over here away from the minimum, because the step size will be very high, because the learning rate is very high in that case, right? You may say that we can put a smaller learning rate and a constant we can put a smaller constant learning rate, but then it will be taking very long for your model to train and achieve the global minimum, right? If you're taking very smaller learning rate, we will see that learning rate process also when we'll be talking about the hands-on session. I'll be training a model with different learning rates, and we will see how slow or how fast that model achieves the global minimum or achieves the good predictions, right? So let me tell you what is the ideal solution, or what is the recommended solution for learning rates in this case. The most recommended solution in learning rates in this case is to start up with a higher learning rate, and then go on decreasing the learning rate as we move ahead. Okay, so there are some scheduling policies to do that also. You may have, for those who have worked in this domain, you may have something like reduced learning rate on plateau. So what do you mean by plateau? When the optimization or the steps don't increase. So when we have reached somewhat the local minimum, we want to reduce the learning rate and achieve the global minimum, right? So we start off with a higher learning rate, and we go on decreasing the learning rate if we achieve a local minimum, or as we go ahead towards convergence. That is the very good solution for that. There are other solutions as well, but you can take into consideration this solution. Let's start off with a higher learning rate, and then we go on decreasing the learning rate as you move towards the global minimum. Okay, so that was about the gradient descent and the learning rate concept. Okay, next concept which I wanted to bring up over here is the back propagation. So any course you take in deep learning subject, any book you read about deep learning concepts, back propagation is the core concept that runs behind the training of these neural networks, right? These neural networks work because there is a back propagation algorithm which has been running to train these neural networks. Okay, so what do we mean by backpropagation algorithm? Backpropagation algorithm refers to the algorithms, or the just a second. Yeah, it basically refers to the methods of calculating the gradients of neural network parameters to train it. Okay, so basically what happens in this process is, so there is a forward pass in your model when you train the model, and there is a backward pass in the same model during training process. And during the backward pass, there is some computation known as back propagation that happens. Okay, what is the forward pass? Say for example, if I'm training this neural network right over here, the right hand side neural network, if I'm trying to train over here, and if I start training this neural network, okay, so I'll start with these input features x1 to x5, right? And there will be a forward pass which will try where we'll be setting some random weights in this case. So the W's will be random selected to be there at the beginning. Okay, there can be a random initialization. There can be some other well educated initializations as well, which you will come across, like something like a Hey initialization, or something like a Hey initialization is something, or Xavier initialization or something like that. Okay, let us assume that we have initialized these weights randomly, okay, for the first epoch. So what it will do is it will take a forward pass. So every feature or every data sample will be passed through this model, and it will be going to this final output layer, final output node. Okay, that will be one forward pass. We are going in the forward direction of this neural network, right? Every data point will be taken in the forward direction, so it will be called as a forward pass of the model. Okay, we'll be getting a prediction, right? Obviously, it is the first iteration or the first epoch, so the prediction will not be good at all because we have set the weights to be random, right? So we will try to update the weights now. And how do we update the weights? We do it using the backward pass process. So in the backward pass process, we go from the output layer, right? We take the predictions that we have in the output layer and we go in the backward direction to the input layer. Okay. What do we mean by going in the backward direction? We do the back propagation procedure. We do the back propagation operation, which is nothing but going in the backward direction of your model from the output layer to the input layer. Okay. Okay, let's get back to back propagation. So it refers to the methods of calculating gradients of neural networks parameters to train it. Okay. Um, what do? We when we try to train a particular model, we use back propagation. That means that we traverse the network in the reverse order, right? And in each step and at each layer, we try to find the derivative or the gradients of the parameters that are there at that layer using the chain rule of the calculus, right? Remember the chain rule of the calculus? I put it over here. So if you are trying to find out something like a partial derivatives, say dz by dx, it will be and if you are trying to find the partial derivative in this case, we'll be using the chain rule of over here, like dz by dy multiplied by dy by dx, correct? So this is the chain rule that we have. That is the conventional chain rule that you might have surely come across during mathematical classes and calculus classes. Right? It is very important. The entire backpropagation algorithm and the entire gradient descent algorithm that is being used over here depends on this chain rule, a single rule of the derivative calculus, right? Chain rule algorithms or chain rule process. Okay. So what happens actually, right? What happens when we say that we are doing backpropagation? What actually happens in that case, right? So at each node, we will be finding out the gradient, right? And the gradient will be traversed back using the chain rule, correct? These gradients are very important, right? We will be seeing these gradients when we'll be talking about the practical hands-on session also. How easy it is to use any deep learning Python framework that we have today and find out the gradients. I'll be specifically talking about PyTorch today, which is a very good example, or which is a very good library to talk about gradients. There is a huge support for gradients computation, and it's very easy to do that, right? We'll be talking about those ahead. But again, the core concept over here is we calculate the gradients at each step and we traverse them back during the training process. Okay. And these gradients are stored during the training process, right? Because we are going to need them again and again. And that is why whenever you will be starting a deep learning model training, for those who have worked on this already, if you are using your GPU for training the deep learning model, you can see that the memory usage of the GPU to be very high, right? Your deep learning model can be something like a 10 MB model or 50 MB model or 100 MB model. But when you're trying to train a model, it can go even something like a 1 GB or 2 GB of space. Why does it do so? Because when we are training a model, we are training the model using gradients. And these gradients are stored in the GPU during the training process because they are needed for those operations. and these are mathematical values. This can be, say, one value can be a float value. It can be a float 32 values. It can take around say 4 bytes, 8 bytes of memory, right? So these are very huge in very extensive in computation. That's why we run the training process on GPU, because it is very computationally expensive, right? And these values are computed at each layer, at each neuron, so it's very memory expensive as well, right? So this is a simple diagram which I have put over here on the right hand side to explain the backpropagation. There was a paper which was published recently in June 2020 by Ujit and the other authors for changing or modifying some of the parameters in the backpropagation process, but they have mentioned a good diagram in this case, right? So this is what explains what a backpropagation actually means, right? Say, for example, you have the input layer neurons X1 and X2. You have U1 and U2 as the hidden layer neurons, and you have one gives you this one gives you the loss functions. The loss function over here finds out the errors between the del target and the actual del that has been there or find out by this model. Okay, we find out the loss function and we take the gradient of this loss function with respect to the function of this particular neuron, right? And when we say that we are back propagating those gradients, we are finding out the gradients of each of the weights with respect to these neurons, right? So again, when we are saying that we have to find out these weights, we'll again back propagate it back to this, right? So we are back propagating the gradients, and when we say that we can see this in all the paths behind, right? So in this path also, in the path at the top also, in the path at the bottom also, we are calculating the gradients and we are traversing them back, right? You can see that we are going till the end of the input, right? So we are traversing the gradients back, and in each of the we will see this gradients process again when we are talking about the hands-on session, and how these gradients are used for updating the weights of the model during training, right? These gradients are very useful, are extremely useful when we are trying to train a model, because it will be these gradients that will be used to update the weights, right? We start off with something like a random weights and we try to attain optimization with that, and that is only possible because we have these gradients with us, right? These are very important concepts, and you can read more about backpropagation if it's not very clear, because these are very important. This is still a there's just one hidden layer in this diagram, but when we are talking about deeper neural networks, something like CNNs, something like an autoencoder, these are very huge and very deep neural networks, but the concept remains the same, right? When we are training such huge models, such deep models, the concept remains the same. The backpropagation process is going to be there, right? There is no running away from that. It's obviously going to be there, and it forms the backbone of the entire training process, correct? So that was about the backpropagation and the gradient descent. Again, I'll reiterate what I these are very important concepts, and that's why I wanted to bring up these points over here. Again, we will see what just a quick recap. Gradient descent, it's an iterative optimization algorithm, right? Every single step that we take towards attaining the global minima is based on the gradient descent algorithm, right? Again, there are many optimization algorithms that are out there, very readily available in any of the libraries like Keras or PyTorch or something like that. But stochastic gradient descent, or mini batch stochastic gradient descent to be very specific, is the most widely used, and it is very easy to understand. And every other algorithm that has been found out or published in papers is based on these concepts, right? So just two steps in that. First is to compute the slope, and then second is to move in the negative direction of the slope by a particular value called as the step value. Okay. Mini batch stochastic gradient descent is most widely used, where what we do is, as you can understand from the name, mini batch is to find out small batches of the data from the data from the entire data set, and using it using stochasticity. So using random, we will be finding out random mini batches or random small batches from the data sets, and then using it for the gradient descent optimization process. And in after finding out the yeah, using the after finding out the derivatives or the gradients for each of the mini batch, we will be updating the weights of the model. Okay. So you can see the diagram also over here, which will explain that those steps. And backpropagation, again, as we spend some time on it, backpropagation is very important in training a neural network. Okay, what we do in this case is we take the partial derivatives and we follow a simple chain rule of the calculus, right? We follow a simple chain rule, and we will be using these gradients to find out the or to update the weights of each of these layers, right? So if we come across these concepts or these terminologies in any paper, remember that these are nothing but different ways of training a model, in which a model starts off with some x value and we want to achieve a y value, and how do we go from x to y is something that is done by these two concepts, right? We also learned something about the learning rate, right? We are learning rate. I not put it in the slide over here, but learning rate is a fairly easy concept. It basically, as the name suggests, learning rate, it basically means how fast or how slow do we want your model to learn, right? If we set the learning rate to be very high, okay, and if you look at this diagram on the left hand side over here, if we set the learning rate to be very high, it will be jumping across these functions very infrequently, right? And it will be very hard to achieve global minima in that case. If we set the learning rate to be very low, it will take a lot of time to train the model, and it will be a computational expensive process. It will be a memory expensive process, and so on. And you don't want to set the learning rate to be very low for if you want to achieve global minima, right? So as I said, what is the recommended way to do that? The most easiest solution out there is to start off with a fairly higher learning rate, okay, and then go on decreasing the learning rate as we move ahead and achieve the global minimum, right? Because as we move closer over here, as you can see from this diagram also, on the diagram on the left hand side also, you can see the sizes of the arrows going down and down, going low, decreasing as we move ahead towards global minimum. What the author wants to mention, or what the author wants to notate over here, is the steps, or the step size, right? Or the value by which we go towards the global minimum. The value should decrease if we want to achieve the global minimum, because the more and more we go towards the minimum, the more and more the value should decrease, ideally, because if you want to achieve the final global minima, otherwise you'll be stuck somewhere in the local minima, and that will not be the ideal convergence that you want to achieve, right? So this was about the gradient descent and backpropagation. Okay, there is another concept called as activation functions, okay, which I wanted to bring up today. Activation functions, this is the a very important concept that we saw on the first slide as well, that these are the decisive operators which actually decides whether the neuron should be activated or not, right? And these are all differentiable operators, right? When I say differentiable, we can find the derivatives of those functions. So we want these operators to be differentiable, and these forms the the basis for deciding whether the neuron should be activated or not, right? So activation functions, they need to have two properties. Any function can become an activation function if these two properties are satisfied, right? First one is that it should be differentiable, and second one is that it should be a non-linear activation function. Why do we say that it should be differentiable? See, because we need this activation function when we are calculating gradients, right? When we are doing backpropagation. See, let me go back to the previous slide. See, if you look at the diagram on the right hand side, if we want to find out the gradients for this particular neuron, we will need the activation function to be computed over here, and we will need the derivative of the activation function also, because that is the ultimate decision making process, right? That's why it is said over here that the activation functions should be differentiable, right? So every neuron will have an activation function, or every layer, the neuron in each layer will have an activation function associated with it, right? And these activation functions should be differentiable, because we will be needing the gradients of those functions, or the gradients of those neurons, when we will be backpropagating for the training process, correct? Second thing is the non-linear characteristic. We want the activation function to be non-linear. And why do we do so? We want it to be non-linear because we want the model to learn the non-linearity in a data set, right? There have been many such activation functions that have been published in the last decade, I guess, which are focusing more on the non-linear characteristic. There are some linear activation functions also, something like a unit activation, right? There are some linear activation functions also. It's not that it is not going to be an activation function. So differentiable is the necessary characteristic non-linear is the desirable characteristic, as I can say. What is the advantage that we get in case of non-linear activation functions, right? So your data is not always going to be a linearly separable or linear distributed data. The data can have a non-linear distribution as well, right? And in that case, the non-linearity in the data set would be handled with the help of your non-linear activation functions. Right? What are some non-linear activation functions? The concept will get clear to you when you will be seeing those. Right? So here I have put some the most prominently used activation functions. Again, I've taken this from a different blog on Medium. You can just search for the Google search on this image, so you can get the blog directly. So in this case, we have some of the most widely used activation functions in this diagram, right? I think the first activation function which made a lot of hike was the sigmoid activation function, right? So you can see that sigmoid the sigmoid function in the calculus is simple as the formula given over here, like 1/1 plus e power minus x, right? But if you look at the curve of this particular function, you can see that the more we move towards the origin, or the more we move towards the point zero, the value of the curve increases and shoots up. But it will be doing it in a smooth fashion, right? And the way it reaches one, it becomes stagnant again, right? Tan H activation function is again a different variation of the sigmoid, where we don't start, or the values are not always non-negative. We can go in the negative direction also. So we are training, or we are starting from -1 to 1 in this case.
Also, okay, you can decide it. Okay, so and here you can calculate the probability to choose the cluster procedure. Okay, so what type of cluster model you design? Yes, you can just calculate and you method design for the cluster method, and you can form the clusters. Okay, so and after creating this, okay, the cluster message you can
I think
send
there is
to
a
the
noise in
entire
this.
network, and choose the current node as. Okay, so if I am connected already with one cluster here, okay, I can consider the current information. So which node is suits.
Okay, I think there was a noise in that case. Okay, sorry for this. Okay, so as I was saying that this was the sigmoid activation function which I was trying to tell you. Then there is something called as tan H activation function, where the values are going in the negative space as well. So we are going from -1 to 1, right? So when we'll be using these activation functions, the data set will also have to be processed in such cases, right? So say if I want to use this activation function on images, right? If I have some images, some natural images, like some images of a cat, dog, etc. And if I want to train a model on these natural images, I will have to process these images, and I will have to normalize those images and bring them in the range of -1 to 1 if I want to use the tan H activation function, because that will be the usual, or it will be the most recommended way to do so. If I want to use sigmoid activation function, I'll have to bring them to a range of 0 to 1, right? I'm talking about the pixel values in those images, right? So based on the activation function, you have to pre-process your data as well, right? So if you know that your activation function is going to put your data in, say, -1 to 1 range, it is better to pre-process those images or those data points in the range of -1 to 1. There are many ways to do so. We will come across those ways as well, where we are normalizing. This process is called as normalization, where we are normalizing the data points in a particular range depending on the activation function that we want to use, right? And then there is something called as a ReLU, right? ReLU is a very popular activation function which is being used in many of the um, computer vision tasks, image processing, deep learning tasks, and even in, say, 1D, the CNN tasks and so on. So ReLU is being extensively used nowadays. Um, I personally don't use sigmoid that much. I personally use TANH and ReLU to a very large extent. You can see the concept of ReLU is pretty simple, right? When we are, if you see at the graph, if you look at the graph of this ReLU, if you see that the points before zero, the function will give you the value as 0, right? So all the negative points will be translated to 0, and all the positive points will be translated to the same value of that positive points, right? It is non-linear function and it is a very simple concept. The formula is also given over there, max of 0 comma x. So if you pass a negative value, the max will be 0, the output will be 0 of that particular function. If you pass something like a 5 or say zero point 0.2, the max of 0 and zero point 0.2 will be 0.2, right? So it's a very simple concept, but a very powerful technique to use these activation functions in the domain. Correct. There's something called as a leaky ReLU as well. Okay, that is a small variation on top of ReLU where we want to go slightly in the negative direction, but not so much. Right. So what we do is we do max of 0.1 comma x, or 0.1 into x, and x. Right. So we are going in the negative direction also. So if we pass negative value in this case, right, say something like a -2 in this case. So if you pass -2, max of minus 0.2, right, and -2, so it will be minus 0.2, right? So we are going in the negative direction by a very small margin, right? If the value of x is in a negative in the negative range, and if we are going in a positive range, we are going according to the value of that particular variable, right? There's something also called as max out and LU. You can see the graphs over here. You can see the formulation over here. Very simple, but these are very important concepts, right? These activation functions are very important concepts when we are trying to train or when we are trying to learn something about the neural networks, right? Because these activation functions are going to be the decision making factors when when we will be deciding whether which neurons should be activated and which layer should be learned and something like that, right? So very important concepts. Very So a brief recap on what we learned till now, right? These are some of the theory points that I wanted to discuss today before moving to some hands-on session. So a brief recap: what we learned today. We learned the general architecture of a neural network, right? What are the weights? What do you mean by weights? What do you mean by a layer? What do you mean by the neurons in each layer? What do you mean by the transfer function? What is the meaning of an activation function? Right? We learned about the different ways in which the neurons can be connected together to form a deep neural network, right? What do you mean by a hidden layer? What is the final function that is being computed because of each layer, each neuron in each layer, right? What is the meaning of a weight associated with that branch and so on, right? We saw those things today. We also saw something like gradient descent algorithm where we want to and propagation algorithm where we are using these algorithms for finding the for the model, right? uh, by training the model, we want to actually achieve the global minimum, and for doing so we need an optimization algorithm, right? Very basic concepts in calculus, but very powerful and very interesting things to do so, right? This forms the basis of the entire deep learning process, deep learning training process that you will come across, right? When you will be training a model, you will not be appreciating these factors, right? Because the high level APIs that we have today, something like Kera, you just do some model.fit function in that case, right? And you don't appreciate what is going on behind when we are trying to train a model. But these processes are very useful, and these forms the backbone of the entire training process. Correct? Very simple concepts, primarily based on the derivative and the chain rule calculus, right? Nothing fancy out there, but these forms the basis of the most advanced recent neural network architecture that have been published recently as well, right? Again, gradient descent is again an optimization algorithm that lets us achieve the global minimum using the different steps that are being taken in the negative direction of the slope, right? Mini batch stochastic gradient descent is the name that I want you guys to remember while leaving off from this session, because this name will come across a lot of times to you. The mini batch stochastic gradient descent, because that forms the basis of the different optimization algorithm that are used today, right? Back propagation algorithm, very useful, or very, I mean, it is the backbone of the entire training process. You can't train a process without, you can't train a model without using back propagation. We find the derivatives at each of the layers in the neural network architecture, and we use the chain rule calculus in that, right, to find out the partial derivatives in each at each step, right? Very important concept. And we also learned about the learning rate parameter, right? Learning rate is usually a hyperparameter in these cases. By hyperparameter, I mean that there is no fixed value of this learning rate variable. You have to determine the value based on the data set that you have, the problem that you are trying to solve, and the model that you are trying to train, right? So you can train your model with different learning rates and find out which suits you the best. That is something which you have to, or which everyone has to experiment with and find out the best learning rate out there. The research paper that you might read obviously suggests a learning rate that you should use, but again, that is up to you if you want to use that, or you can even go on experimenting with different learning rates on your data set and on your neural network and find out the optimum learning rate for your case. So the better the learning rate, the more closer you will be to the global minimum, and that is what we want to try to solve, right? I have practically seen that if we don't use a good learning rate, and if we don't find out the optimal learning rate for the problem that we are trying to solve, we won't be getting a good solution, or we won't be achieving the best results out there, right? So since when I was trying to say solve a problem for say image recognition, right? Say if I want to identify if an image contains a cat or a dog or a mouse or something like that, um, and if I yeah, and if I use a very slight, very small learning rate and a constant learning rate, I never achieved global minima with that. Right? It used to stick around in a particular local minima, as we call, and it never achieved convergence even after thousands of epochs of training. Right? That important. That is how important this learning rate factor is. Right? There are various scheduling policies of this learning rate. Again, as I said, there is something called as reduce learning rate on plateau. So that means that when the loss function is going to achieve plateau, right? The loss function is not changing at all, right? It is going to decrease the learning rate according to that, right? So it is a very intelligent way of tweaking the learning rate based on the loss function values, right? Second thing can be something like a step linear learning rate, where we determine that after every epoch, this is the value by which the learning rate should decrease, right? So there are many such scheduling policies of learning rate and very readily available, but you should understand the mathematical concept behind these scheduling policies and what is the essence of learning rate, right? Then we saw the activation functions, right? So activation functions are the differentiable operators based on which we determine whether the neuron should be activated or not, right? Two important properties of these activation functions: differentiability and nonlinearity, right? With that, what we identified is there are a lot of activation functions that are being used today. Something like a sigmoid activation function, something like a ReLU activation function, tanh activation function, leaky ReLU activation function, and so on. These are different activation functions. You can find the form very useful, and you should understand what is the essence of these algorithms when we try to solve over here. Okay. So next up, we are going to try some hands-on session for the concept that we have learned in this case. I would request that if any of you want to try these concepts with me, or if you want, I'll be opening a Jupyter notebook now, and we'll be learning some basic concepts of PyTorch, and we'll be using the concepts that we learned in this few slides that we saw today for this, and we will be seeing how it behaves, right? That is what we wanted to try with this hands-on session. So we will be starting a hands-on session now, and we will be continuing that hands-on session till something like 12:15, I guess, 12:10 to 12:15. We will take a break at that point of time for 15 minutes, and we'll be resuming back the hands-on session after that. Okay. Now I'll be switching to Jupyter Notebook. So just give me a minute. I want to open the Jupyter Notebook. So just give me a minute. Okay. Okay. Sorry for the delay. Okay. Um, I saw some question coming up in the chat. Okay, Pratik is asking, can we follow on collab? I have this notebook on my local machine. Um, Sorry for the news that I mean, these are corporate laptops, so we can't put these notebooks on Google Colab. But surely you can try this. The code snippet that I'm going to learn over here. These are very short code snippets. So if you can type faster and you can, try to imitate these notebooks on your end on Google Colab, sure, you can definitely try it. There is no dependency on anything as such. Just that when we're talking about some data sets ahead, you will be needing those data sets, and you can. I'll give you the links for the data set also. You can try those data sets as well. Very very small data sets, so it won't take too much time to download them also. But sure, yeah. Thanks for asking, and you can surely try them on your end, definitely. Okay. Okay. So let me just zoom in a bit. Okay, this is fine. Okay. So yeah. Let us start with this hands-on session. For those guys who are just seeing this and are not trying at your end, don't worry. I'll be giving this IPython notebook to Zope sir, and maybe if they can share this with you, it will be good. And if not, I can also post this the simple notebook on my GitHub profile. You can anyway always download this IPython notebook from my GitHub profile and try it at your end. So nothing fancy about this code snippet that I'm going to try and over here, but we want to understand the concepts that we have learned till now, and understand how these concepts work in the real life when we are doing something as simple as model.fit, right? I'm saying this again and again, the model.fit, because it has become a sad reality of the data science fraternity today, that most of the professionals or most of the students who are working in this domain, they don't understand the concepts that are running behind the mathematical or the mathematical concepts that are running behind the high level APIs, right? Keras has somehow spoiled us, right? Because it doesn't let us appreciate the mathematical beauty that runs behind the training process. And that is something, I mean, we can learn about the deeper models and CNNs and GANs and something like that, right? But to appreciate the what happens behind every training process of any neural network, you need to understand these concepts, right? Okay, enough of that. Let us see some basics of PyTorch, right? I'm not an endorser of PyTorch definitely, but what I wanted to do in this session is I wanted to, understand, let you understand the basic concepts of PyTorch, because uh, one advantage of PyTorch is it lets you, get the derivatives and the gradients of variables very easily. Okay, that is an important process. That is a very very useful tool, or a very very useful API for us when we are trying to understand these concepts. That's why I've selected PyTorch over here. You can try the same with Keras. You can try the same with TensorFlow. No issues with that. Any network, any Python framework, you can even try the same things with R. So any framework is fine. You can try the same things in them as well. But I selected PyTorch over here because I have some experience in working with PyTorch, and it is very easy to understand, very easy to follow, and you will appreciate those concepts very nicely when we are trying with PyTorch in this case. Okay. I hope the browser is visible. If not, just put it in the chat box. I'll see if it has not been shared properly. Okay, so let's begin. Right. Basic import steps. We are importing two libraries over here. Okay, thank you, Sonia. So basic import steps. We are importing two libraries over here. Torch, which is basic the PyTorch library, and NumPy library. Okay, I'll execute each cell in front of you. Right. I have now executed the import statements. Right. Before we move forward to the different concepts of PyTorch and using the derivative functions and everything, I wanted you to understand the basics, the operations that we are going to see in today, the basics of these PyTorch values, right? For those who are very new to PyTorch, this will be an important This will be an important 5 to 10 minutes of session where you'll be understanding the basics of PyTorch. For those who have already worked on PyTorch, this will be a refresher session, so don't worry about that, right? So PyTorch is basically, if you go on the documentation page and if you understand, if you read about the first few lines of what PyTorch is, they have very beautifully explained that PyTorch is nothing but giving a GPU compute capability to your NumPy arrays, right? They have mentioned it very precisely that they are going to work on something like tensors, right? What are tensors? Tensors are nothing but the matrices, the arrays, the 2D arrays, ND arrays that we are trying to say. That nothing but tensors, right? Um, so PyTorch, what it does is it operates on these tensors in a very efficient way, right? When I say efficient, it is computationally efficient, it is memory efficient, and it also lets you use the GPU capability to work on these tensors, right? That is the power that PyTorch gives us, right? So any matrix or any array, ND array in this case will be called as tensor, right? Tensor is something which is a very popular convention to understand the matrix operations or the ND array operations in any case. So tensor is what is being used in PyTorch, and same thing will come in TensorFlow as well. That is how the name of TensorFlow came into the picture, right? So what I wanted to show over here is the basic operations, right? Something like, say, if I have a NumPy array of size 10 by 10, right? np.once is a pretty usual function which try to generate a array or a array of size m by n, and it will all the array will contain all the elements as one, right? So what I'm trying to do over here is I'm trying to generate a 10 by 10 array of element of value 1. It will be a D type of float 32 value, right? And I'm trying to generate a tensor from there, right? So that is how the interoperability happens from tensor to from PyTorch to NumPy, right? I'm passing a NumPy array to this function. It will give me something like a variable, right? Execute this thing. See what we got over here. We have got I have printed a dot shape over here. I have printed a dot d type over here. Let me also print what is the type of a. Okay, see. So that what is a over here? A is so this torch dot tensor gives you a tensor as an output to the input that we have given as a parameter in this case. Now, what is the size of this tensor that is being constructed? It is of size 10 by 10. Right? What is the D type of this? What is the data type of this tensor that is being constructed? It is the float 32. So it is the same value that you have put for the NumPy array, and it has propagated the same value to the tensor as well, right? And what is the type of this variable? Now, because we have used torch.tensor as the function, a value or the variable a will also be of type tensor. So that is how we construct a tensor. So if you have a data set in the format of a NumPy array, and if you want to convert it into a tensor for working with PyTorch, this is how it should be, right? This is how you can initialize it, and we can get an array over here. If you want to see what A contains, see this, right? This is a 10 by 10 tensor. Okay, Torch is basically the library that we're talking, like PyTorch. So you can just Google it. So this PyTorch library is something that we are trying to understand over here. It will be very useful for us to understand this library. It is a very popular library. It was actually constructed by the researchers from Facebook. This library is now becoming the de facto standard for different production environments as well. Right? Very useful library. A very easy to use ones and very powerful as well. That is what we are trying to learn today. So when we say import Torch, we are actually importing this library and we are using the functions of this library. Okay, that is what is known as torch over. So we have imported torch over here, right? And we are using the different functions of that torch. Okay. Um, so when we saw the value of the variable a over here, we can see that this is a 10 by 10 array, and the entire array contains element 1, because that is what we initialized over here, right? That is what we initialized over here, right? So this is what the a contains now. Similarly, if I want to randomly initialize a with some value, see this. right? So there's a function in torch which takes in rand as the function. Rand basically it's an abbreviation for random, and you can pass the size of the array that you want, the size of the random array that you want, right? So this is a 2 by 3 array, and you can see that these numbers, I have not fed those numbers. These numbers are taken randomly, right? So these numbers are taken randomly. If I execute this once again the numbers will change, right? So as many times I execute this, the numbers are going to change because this is a random function, right? If you see the documentation of this torch.rand, it is taking these numbers from a random distribution, right? From a random uniform distribution. So every number from say a particular range of 0 to 1, for example, will be given equal chances of being in this array, right? So a very useful tool if you want to debug your model with some random values, or if you want to test your operations with some random values. This is a good function which you can pass simply the shape of the matrix, or the shape of the array that you want, or the tensor that you want, and it will give you a random variable, right? um, uh, uh, Again, this is a transpose operation which is very useful. See, when we're talking about let me just bring up the PPT again. Okay, sorry for the switch, but I want to you to all to appreciate the transpose function, right? So when we are talking about these operations, right, something like wij xi plus bj, okay, when we say wixi or wijxi, we are multiplying two different vectors, right? You must have remembered the vector calculus or the vector operations, right? When we multiply two vectors with each other, say wij is also going to be a vector, xi is also going to be a vector, and when we multiply two vectors with each other, we are actually doing wi transpose xi, right? We calculate the transpose of one vector and then do a dot product of that with the second vector, and that is how important the transpose function is. Okay, we also saw the transpose function, or whenever you will be learning the conventional machine learning algorithms like SVMs or KNNs or something like that, you'll be coming across this transpose operation pretty frequently, right? So that is how the important this transpose operation is. Any any vector multiplication that you will come across, you will have to follow the transpose operation. You will have to use the transpose operation that is being used internally. Okay, so that is how, yeah, so that is as simple as this. Take any tensor and do a dot capital T in front of it, and it will give you a transpose of this tensor, right? So see, my A value was something of dimension 2 cross 3, so 2 rows and 3 columns, right? When I do a transpose operation on top of it, I get a transpose of that matrix, something like 3 cross 2, right? 3 rows and 2 columns, and then I have the values in that order equally, right? So simple of this, right? You just have to do dot uppercase T, and you will get the transpose of these operations, right? Simple. Important characteristic is the interoperability with NumPy, right? As I said, that it is so simple to take any variable which is already there in the NumPy format and use it in the tensor format in this PyTorch library. See, if you look at this snippet, if I am building a NumPy array with this np.random.random of size 2 by 3, again, A will be a NumPy array, a randomly initialized NumPy array of size 2 by 3. What I will be doing is there is a function called as from numpy, right? This is a very memory efficient function. I'll tell you why this is memory efficient function. What I'm doing over here is toss.from numpy. So if I use from numpy function, and if I pass this a variable over here, which is being considered, which is actually a numpy array, randomly initialized, c will be a tensor. C will be a tensor that I'll be getting, which will be exactly equal to this numpy array, right? Let me just execute this thing. See, what happened over here is we initialize the a with a random variables. We initialize c with the same numpy array, but we convert it into a tensor using from numpy function. Very useful function. I'll tell you why. Right. So a, as usual, as expected, it is a numpy array, and c, as expected, it is a tensor array. If I print the values of these two guys, right? See the values, right? A was a numpy array, so in numpy array the precision is very high, right? Because numpy was used or is being used for mathematically extensive operations and statistical operations. So you can see that it is going up to something like 8th decimal, right? But when we do toss dot from numpy, it Yeah, so it is going only up to fourth decimal. Okay, so it is doing some sort of optimization or rounding up of values to the fourth decimal while doing so. Although the data type remains the same, right? The torch data type is still the same. So, but still it is doing some roundup operations to save memory and to ease the computation when we are going ahead. Okay, so you can see the values are exactly the same, just in a rounded up version, right? Now see the memory management over here. This is a very important concept and very useful one as well, which and this is why I love PyTorch. The memory management function or memory efficiency is very high in this case, right? Say I had created this value, right? I had created this variable a over here, which is this thing, right? You can say that this is the value of a, right? The one which I've highlighted over here. Now, if I change the value of any particular element in this array, right? So for example, if I change the value in the first row and second column. So first row essentially means we start from zero, right? So we essentially means the this particular value, right? This 0.13 will be the value which we are trying to change over here. And if I set this value as 10, okay, let me just execute it and print the value of a after that. See, this is where we started, right? Very simple. This is where we started, and we are now just changing the we are just changing the value of this particular variable. Sorry, yeah, this particular variable from 0.1304 to 10. Okay, this was expected. Very good. We have changed the value of this thing now. But how did it reflect with C? Right? C was created from A, right? When we do this torch dot from numpy, C was created from A, right? So what happens when we do this? When we change any variable, any value in A, how does it reflect in C? C. The value in the C is also getting changed, right? And that is the memory efficiency, which I call it. This essentially means that C is nothing but a reference variable to the numpy variable A, right? So the memory management operation, as we see, we don't have to extensively do that in case of PyTorch. These are all pointing out to the same variable, and they are just doing some sort of a memory efficiency operation, so that if you change the values in A, it is going to change the values in C as well, right? Very easy. What happens if we change the value in C? Let us check, right? So for example, if I change the value in C to be something like 5, okay, and let us print C after that. See, I've changed the value in 5. Okay. And now if I see the value in A, okay, see this, right? The value in A is also changed because of that. So basically A and C are not pointing to two different memory locations, right? That is the memory efficiency that happens when you are using PyTorch. It is so memory efficient that when you are trying to, if you are trying to interoperate between PyTorch and NumPy, it is not going to create different variables, right? This is just a matrix of size 2 cross 3, right? But when we are trying to do something like an image processing tasks, where we are trying to operate on images of size 256 by 256 or 128 by 128, or say even if 3 channel output, so 3 by 128 by 128 or 3 by 56 by 256, these are going to be huge matrices. And if we are using such memory efficient operations, look at the memory that is going to be saved because of that, right? So these are very useful techniques, very efficient techniques to save your memory, and very useful when we are trying to solve such computationally extensive problems, right? So this is what I wanted to let you guys know, that this is the memory efficiency is very high in this case. Now let's talk about the gradient operations. So gradient is what we have been hearing from morning now today. That gradient forms the basis of different algorithms like backpropagation, gradient descent, etc. But as I said, the reason why I'm choosing PyTorch for this session for you guys to know is the support that we have for gradient operations in this, right? That is what I wanted to showcase over here, right? Very easy and very easy to follow, right? So let us check how this behaves, right? What I have tried over here is I have tried to construct a tensor. Let me just put this in a different cell so that you guys can appreciate it differently. Okay. So yeah, let us just look at this tensor. Okay, just focus on this tensor. X equal to torch.tensor, and this is the value that I have put in this tensor, right? 1 minus 2, 3 comma 1. Look at this flag over here. requires grad equal to true. Okay, so requires grad equal to true is kind of a flag which tells the PyTorch library that you need to compute gradients on this variable. Okay, whenever I'll be using a function called as backward, I'll be using that function called as backward. We will have to, the PyTorch library will understand that yes, I have to compute the gradients on these variables also. Okay, this is a very important flag. If you set this flag to false, you are not going to the PyTorch library is not going to compute gradients on this variable. Why does it do so? So by default, the value of this requires grad is false, and that is because computationally extensive operation of gradient computation, right? It is not going to unnecessarily find out the derivatives or the gradients of different variables and store them in the memory. No, if you want the gradients, you need to set that flag to true, and then it will compute the gradients and store them in the memory. Otherwise, it is not going to do so. So very useful flag, very easy to do so, but we'll see how powerful this is, right? So this is the x value which I have put over here, 1 minus 2, 3, comma 1. Okay, and this is the simple explanation or simple how do you say, a simple equation or a simple function that I wanted to put over here. Okay, what is output over here? It is 3 into x to the power of 2 plus 5x, right? If we look in the mathematical terms, it is 3x plus 5x, right? Let me call as y. So you might have, so see, so it is such a simple operation. 3x square plus 5x, right? When we are trying to solve any mathematical problem, or when we are trying to do a deep learning solution, we are actually solving an optimization problem, which can be a linear equation, which can be a polynomial equation, which can be a quadratic equation, it can be anything. So we are trying to solve a particular equation when we are trying to do that, when we are trying to solve these problems, right? Let us here put a very easy example of this equation 3x square plus 5x, because I wanted you guys to understand what is the power of this gradient operations in PyTorch, or in any case in general, right? Let us see how these gradients are calculated, right? So when I do 3x square plus 5x, right, it will take the value of x from the top, right, this thing, and it will do 3x square plus 5x in this case. Um, then what I do is I calculate the sum over here, right, for the value that I will be getting from there, and then the final value of out will be that particular sum. Let me just execute it and we'll go. Sorry. Okay, I have not executed it. So I will execute this thing. Okay, then let me execute this. Okay. So if you see this, this first tensor that gets printed over here is from this particular print function over here, print statement over here, right? 3x square plus 5x. If you substitute x in this equation, 1 minus 2, 3, 1. If I do square of that, it will be 1, 4, 9, 1 into 3. So it will be 3, 12, 27, 3 plus 5x, right? So it will be something around this. This is going to be true, obviously. So the output of the first statement would be something like this: 8, 2, 42, and 8. The matrix, this thing. Okay. Next step, what we do over here is we do the sum of this, right? Some of this function that we have, some of this metric that we have got over here. This is a reduction step, right? You can do mean over here as well, which will be taking mean from all these values. You can do a sum over here as well that we have done over here, which will be taking sum of all these values, and that is what we have got as the output over here. See the output over here, 60. If you do the sum of all these variables or all these elements, you will find the output as 60. Correct? See the grad function variable in this case. See, add backward 0, sum backward 0, right? Why is it taking add backward 0? Because of this operation. Why is it taking sum backward 0? Because of this operation, right? It is a kind of a notation that PyTorch uses in itself, that yes, the gradients are getting computed now. Okay, every operation that we do over here, the gradients are going to be computed when we will doing a backward function. There is a backward function associated with that. See, next step is the same thing. I'll just be doing out dot backward. This function is not going to return any value to me, but if you look at the grad property of any variable that we'll be seeing now, you will be seeing that it has computed the gradients for each case. Okay, we'll see that. Let me just execute out dot backward. Okay, I've executed out dot backward now. Now if I tell you that can you find out the partial derivative of output with respect to x, the partial derivative of output with respect to x, right? So if you see this output equal to 3x square plus 5x, right? If I find out the partial derivative of this 3x square plus 5x, going back to the high school calculus, 3x square plus 5x will be 6x plus 5, right? 6 6x plus 5, right? So I'll just do x stat grad. So I have not calculated anything on my own. I have just done out dot backward in this case, right? And now there is a variable called as, or the attribute called as grad for every tensor. X was a tensor. There is an attribute called as grad. Let us see what this attribute contains. See this value, right? You must be wondering what this value is. If I do 6x plus 5, see this value, right? So this value, when I do x dot grad, this value is nothing but the derivative of output with respect to x, right? Very simple. You can do it manually as well. That is what I've done over here. 6x plus 5, same value, right? Same value over here. So that is the power of that is the power of PyTorch library, that it lets you compute gradients without even worrying about it. You just have to set a flag called requires grad equal to true in the beginning. That's it. No matter how complex your function is, here it's a very simple quadratic equation over here that I've used here, 3x squared plus 5x. No matter how computationally expensive or how complex your equation is, it is going to compute the gradient. Say this is just a one variable over here, right? Here I have just used x over here. There can be many such variables, and that is what happens when we are trying to train neural networks. There are so many variables, and we have to, we don't have to worry about calculating gradients of those variables at all. PyTorch does it on its own, right? That is what the advantage over here. So this is a very important function. Autograd or the grad property is a very important property over here, which you can find out. Just do x dot grad and it will give you the gradient of that thing, right? So okay, backward function. What when we say backward function, it is nothing but the backward pass that we observed in the slide that we observed today, right? Very simple explanation. When we do backward, out dot backward, it actually calculates gradients for all the variables that are there in the output function, where the requires grad function or where the requires grad flag was set to true. Okay, it doesn't do any operation on output as such. It is just a way of telling, or it is just a way of mentioning in the PyTorch that I need to calculate gradients in all the supported variables, right? That is what it does. It is not doing any operation on out or any changes to out variable. It is just calculating gradients for all the functions, right? For all the variables supported to it. And that is how this happened, right? If I don't do out dot backward, I won't be getting this, right? If you want to see, we will just see. I'll just restart the kernel so that we will be saving this thing. Okay, yeah. So if I do this, if I do this, torch is not defined. Yeah. So if I do this, okay, this is done. Requires grad equal to true. I have put this over here, right? I won't do out dot backward. Now I'll straight away go to here, x dot grad. Didn't return anything. I've executed this. See, it is not returning anything. I've executed this, right? Because we have not executed the backward function. Backward function execution steps mentions that the PyTorch needs to calculate gradient for each of the variable where the require grad flag was set to true. Now when I set this function, or now when I call this function, okay, out dot backward, and now when I find the value of x dot grad, now it has the derivative, right? So unless and until you execute this function, it is not going to compute the derivative, right? That is a way of telling the PyTorch that yes, I want to compute the derivatives now. Okay, simple explanation, but this is a very important step when we are trying to train a particular neural network, because without backward pass or without computing gradients, there is no neural network that you can train over here, right? Very
Can you
important step.
just repeat this again, like out dot backward again? I mean,
Yeah. Okay. I'll just show you guys like what happened over here actually. So when I did, when I computed the value of out over here, out is actually a function that I have written over here, 3x squared plus 5x, right? When I did out dot backward, right? Out.backward is a way of telling PyTorch, or it is a function which executes the gradients, or which computes the gradients of all the dependent variables, in this case in the pipeline, right? Without passing or without calling the backward function, the PyTorch library is not going to compute the gradients for those, right? Because it is not it is not going to compute the gradient, because it is mathematically expensive. It is expensive in the memory perspective also. So unless and until you compute this function, unless and until you call this function, the gradients are not going to get computed. So this is just a simple function which tells the library to compute the gradients. That's it. Okay, I'll just repeat what I demonstrate what I have done over here. Okay, I'll just restart the kernel so that it doesn't stores the value in the memory, right? And I'll just import torch here. I don't have to jump again. Okay, now what I've done here, I have this tensor called as, I'll just clear the outputs for you guys. Okay, I'll repeat again. I have this tensor tensor x, and I have this output variable, simple output variable. It is using this function 3x square plus 5x, and then doing a sum of this, right? If I do a sum of this is what I'm going to learn, right? See now what I'm trying to do. If I don't execute this function, right, I'm skipping this step. I'm skipping the backward function step, and I'm trying to attain, I'm trying to get the value of the attribute grad over here of the variable x, right? I'm skipping this step, right? And if I'm just trying to execute this thing, right? See, it doesn't return anything. It is not returning anything because there is no gradient that has been computed till now. Although the variable out is has been operated on, but the gradient has not been computed. The gradients will only be computed when we execute backward function. Okay, see, if I execute this grad again and again, it is not going to return me anything because the gradients have not been computed till now. Now when I do this, now when I do out dot backward, let me do this. Yes, now I have done out dot backward, and now when I do x dot grad, now it is going to return me gradients, right? So in layman terms, the backward function is a way of telling PyTorch that I want to compute the derivatives of the variables associated with that variable, right? So this can be in the terms of neural networks, this can be an output function at the last layer in your neural network, the output variable, right? And if you want to compute the gradients of all the neurons in the hidden layers, you just have to do out dot backward. A simple out dot backward call will compute the gradients of all the neurons or of all the hidden layers in your neural network, right?
I
That is a
I have
simple.
a question here. Like this out dot backward is calculating only like from the output layer to the input layer, right? It's not only for the hidden layer. It's like from the output to the input layer, including hidden also.
Yes, yes, including hidden also. Yeah. So
Okay,
because
thank you.
the partial derivatives of the hidden layers will be calculated in that case, right? So because without that we won't be getting the chain rule of the derivative that we have learned in the differentiation function, right? So whenever we'll be learning this or whenever we'll be executing this backward function, it is not only going to compute the derivative for the output to the hidden layer, it is going to compute a derivative across the neural network, right? For every parameter where we have set the requires grad function variable to true. Okay, that is how it does. Okay, so this was about the grad function and the derivatives variables that we have seen till now. This is going to be very important for us when we'll be learning this thing. Next up is a cackle problem which I wanted to cover. Okay, but I think it's 12:10, so let us take a break now. Okay, once we come back from the break, I'll be I'll be taking a hands-on session of training a model on this problem, on a Kaggle house price prediction problem, using a simple mathematical operations using what we have learned today versus using an API from PyTorch, right? So what is usually used in the industry versus what happens behind the hood or under the hood is what I'll be comparing with that. Okay, that will be the first part of the session. After coming back from the break, second part would be I'll be running you across some of the recent trends in the neural network architecture fraternity, where new architectures which are making news and which are becoming very very popular in the domain. I'll be covering some of them. Okay, so we'll be taking break now. Let us reconvene at say 12:30. Okay, 20 minutes break would be fine, right? So let us reconvene at 12:30. Yes, good point. I'll be giving the data set link over here. It will be useful for us so that you can, replicate these at your end. So I'll be putting the data set link in the chat box. You can download the data set and keep it at your end so that we can compute things simultaneously. Sure. Okay. Let's just
Yeah,
reconvene at 12:30. Okay.
yeah, no problem, Rohan.
Sure.
Chalega.
Thank you, sir. Okay.
Yeah. Okay, all the participants take a tea break for 20 minutes, no problem. So please resume it at 12:30 sharp. Thank you.